For any homework-related queries, call us at +1 678 648 4277. You can mail us at support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or reach us at www.computernetworkassignmenthelp.com. Problem 1. INDCCA Alice and Bob have taken 6.857 and would like to send confidential messages to each other in a way that meets the INDCCA definition given there. Bob suggests the following method. Let ENC K, M denote the process of padding M with a 1-bit and then as many 0 bits as needed to make the message length a multiple of 128 bits, and then using AES in CBC mode to encrypt the result, using a randomly chosen 128-bit 4. The result is ENC K, M equals 4, C1, C2, Cn. Let rev S denote the reverse of a sequence S. That is, S is parsed as a sequence of 128-bit blocks. The length of S must be a multiple of 128 bits, and these blocks are rearranged into reverse order. Bob then proposes that he and Alice secretly agree on 2 AES keys K1 and K2, and then define the encryption of a message M as computernetworkassignmenthelp.com. K1 K2 M equals ENC K2 rev ENC K1 M. The intent here is that the reversal avoids the problem noted in class, that ciphertext prefixes decode as prefixes of the message. Show that this method does not meet the INDCCA security definition given in class. That is, show how the adversary can win the security game against this method. Problem 2. Counts. Ben Bitdiddle has designed a new cryptosystem called Counts, but we suspect it might not be as strong as we would like to be. Therefore, we ask your help to break it. In this problem, we will be working with a finite field GF16. The elements of our field are all 4-bit strings. The F-yield addition is computed as XOR GF16 X plus GF16 Y equals GF16 X circled plus Y. We provide the 2 tables describing addition and multiplication laws on the course webpage. If you are curious, these tables are obtained by interpreting 4-bit field elements as degree less than or equal to 4 polynomials for over GF2 and performing addition and multiplication modulo the irreducible polynomial x plus 1. ComputerNetworkAssignmentHelp.com. However, for the purposes of this problem, you do not need to understand how our GF16 is constructed. The solutions we know assume black box access to GF16. We have provided a GF16 implementation for you. Counts is a 64-bit block cipher. The secret key consists of 3 parts. An invertible 16 by 16 matrix A over GF16, a 16-element vector B over GF16, and a permutation, bijection, S that maps GF16 1-to-1 and onto GF16. To encrypt a 64-bit block B, we first break it up in 16 4-bit chunks and interpret each of them as a GF16 element. So block B corresponds to length 16 vector X equals X0, X15 over GF16. The encryptions consists of the following. Y equals S, AX plus B, where the permutation S is individually applied to each of 16 elements of V equals AX plus B. The 16-element vector Y is later reinterpreted as 64-bit integer to obtain the encrypted block B. Ben suspects that his cryptosystem is very secure. After all, it has around 16162 possible keys. However, we suspect that there are many equivalent keys. These keys have different values for A, B, S, but produce the same ciphertext for any given plaintext. Is our suspicion well-founded? Computer Network Assignment Help.com. B. Describe a chosen ciphertext attack on CALMS that recovers the unknown key A, B, S, or an equivalent key. C. To demonstrate that your attack works, write an implementation that can break a randomly generated key. We have set up a web server that implements CALMS algorithm at prove that your implementation works by getting your team's name on the list of successful teams. The server is powered by scripts.mit.edu shared hosting infrastructure. Please don't issue denial of service attacks or try to attack their servers. Computer Network Assignment Help.com. Solution 1. INDCCA. Theorem: Bob's method E is not INDCCA secure. Proof: the adversary picks M0 equals 0x, M1 equals 1x for large x greater than or equal to 3, 1, 28 in phase I. Then y equals EK1, K2, MD. Let z equals y with the first bit flipped. Since z equals y, the adversary is allowed to ask for dk1, k2, z in phase 2. This correctly gives the first 128-bit block of MD, revealing D, zeros if D equals 0 or ones if D equals 1. Therefore, the adversary wins the game. Why does this work? Consider the steps of E, where MD is divided into n 128-bit blocks, n greater than or equal to 3. 1. Start with MD equals M1 SAMN. 1, 1, 2. ENCBCK1, M1, 1, MN equals 4, C1 CN. 3 Rev 4 1 1 1 1 1 C1 CN equals CN C4 1 1. ENCBC 1 1 1 2 2 2 2 4. K2 CN C1 4 equals 4 C1 CN CN plus 1. 2 2 2 5. End with 4, 2, C1 CN, CN plus 1 equals Y. Computer Network Assignment Help.com. Now, consider the steps of D, which reverses E. 1. Start with Y equals 4, 2, C1 CN, CN plus 1. Dec CBC 2. K2, 4, C1, CN, CN plus 1, equals CN, C4, 1, 1. 3, Rev, CN, C1, 4, 1, equals 4, 1, C1, CN. 4, Dec CBCK1, 4, 1, C1, CN, equals M1, MN. 5, End with M1, MN equals MD. Finally, consider the steps of D when the input is Z instead of Y, the first bit is flipped. Denote any changed blocks in red. As we observed in Lecture 9, the bit flip only affects the decryption of the current block and the next block, since each decrypted block only depends on CI and CI1, and only the first block depends on 4. 1. Start with Z equals 4, 2, C1, 2, CN, 2, CN plus 1, 2. 2, Dec CBCK2, 4, 2, C1, 2, CN, 2, CN plus 1, 2 equals CN, C1, 4, 1. 3, Rev, CN, C4, 1, 1 equals 4, 1, C1, CN. 4, Dec CBC, 1, K1, 4, C1, CN equals M.